Look at the objects around you. For a long time, physics treated the universe like it had two completely separate ledgers. On one side, you had mass, the physical stuff, the atoms. On the other side, you had energy, the heat, the light, and the force you apply to move that stuff. For centuries, physics operated on the belief that these two accounts never mixed. You could burn a log or push a boulder, converting one type of energy into another, but the physical mass remained a separate category of existence. Then, in 1905, Albert Einstein published his theory of special relativity and collapsed that dualistic worldview. Einstein proposed that mass is actually highly concentrated, congealed energy. These two categories are a single continuum. Under the right conditions, physical matter converts directly into energy, and energy can condense back into mass. This realization meant that every ordinary object, a coffee cup, a textbook, a block of wood, acts as a massive reservoir of dormant power. This equivalence is expressed in the most famous mathematical equation in history, E equals mc squared. Here, E is the total energy equivalent, and m is the mass of the object. They sit on opposite sides of the equal sign, meaning they scale directly with one another. The secret to the equation's immense power lies in that c. That stands for the velocity of light in a vacuum, roughly 300 million meters per second. Einstein's formula requires you to square that velocity. When you multiply 300 million by 300 million, you get a 9 with 16 zeros after it. This acts as the conversion rate between mass and energy. Because this squared multiplier is so huge, even a microscopic speck of mass translates into enough energy to power a city. To see exactly how much power we are talking about, let's look at the math for a tiny everyday amount of matter, exactly 1 gram. Think of a single paperclip. Next, we can compare this to a conventional chemical reaction, like burning fossil fuels. A large industrial plant burning a full kilogram of coal generates about 10 million joules of heat. But unlocking the mass energy in our single paperclip-sized gram generates millions of times more power than that. If humanity can trigger this conversion, a literal pinhead of matter contains enough power to rival tons of conventional fuel. The math is clear, but where does this mass-to-energy conversion actually occur in nature? It actually happens at the very center of the atom. Einstein's principles are the engine governing the nucleus. Physicists can verify a phenomenon called the mass defect. A fully assembled nucleus weighs slightly less than the sum of its individual separated protons and neutrons. That missing mass reappears as nuclear binding energy, the force holding repelling protons together in a tight cluster. We harness this in fission by breaking apart heavy nuclei into smaller fragments. Because those smaller fragments are more tightly bound, their total mass is lower than the original nucleus. The difference, that tiny fraction of lost mass, is released as the enormous heat and radiation we use to generate electricity. By writing down 3 letters and a number, Einstein permanently altered humanity's understanding of the physical universe. We learned that generating massive amounts of power does not require digging up mountains of physical resources or relying on weak chemical bonds. The greatest energy reserves in the cosmos are locked entirely within the microscopic, structural changes of the atom. E equals mc squared proved that every single speck of matter is a sleeping giant of cosmic energy, waiting to be awakened.